Populations and ecosystems. This video covers looking at population ecology, so specifically looking at the factors that affect how quickly a population of organisms actually grows. The key concepts you should get after watching this video is what are the characteristics of a population, what do we actually use to define a population, what are the two types of population growth and what do the graphs look like for each of them, and what is the definition of a carrying capacity for a population in a certain environment. And finally, we'll go over the two types of limiting factors, and you'll need to know the examples of each. A group of the same kind of organism that lives in the same place is called you should know, a population. There are three important characteristics that we look at to define a population. The first is that we look at the geographic distribution of or range. So where are they actually found in the world? Are they found in the forest? Are they found in the desert? We look at the population density. So we look at the number of individuals per unit area. Are there 20 individuals within a 1 mile radius? Or are there 1,000 individuals within a 1 inch radius? So that is population density. And finally, we look at growth rate, how quickly you're actually growing. As I mentioned, density is the number of individuals per unit area, which really depends on the species and its ecosystem. So depending on the species, you might have certain species that love to live in clumped distributions, so they like living in family units or together around each other. Or you might be a species that is very spread out. So that is what density means, just how many individuals do you have in a certain amount of area. So is this high or low density? Clearly it's high density. You can see all of the animals that are very clumped together, living almost on top of each other. High or low density, obviously very low density since they're very spread out. They're not really on top of each other. Let's now discuss population growth. So there's three main factors that affect how the actual size of a population. They're very common sense. The first one is the number of births you have in your population. Then you have the number of deaths. And finally, you have the number of individuals that enter or immigrate into your population. And you have the number of individuals that leave or emigrate out of your population. Easiest way to remember the difference is when you go into a population, it's immigration. So you immigrate into the United States. And when you are leaving your population, you're exiting. So you emigrated from Germany to the United States. So immigration is entering the population, emigration is leaving. And it makes perfect sense that a population is going to grow when the birth rate is greater than the death rate, or that the birth rate and the immigration rate is greater than the emigration rate plus the death rate. It's actually interesting that in the United States, our population is still growing, but it is not due to the number of births. We've actually stabilized with the amount of births. It's actually due to our immigration. So we keep allowing people to come in from other countries, so our population keeps increasing, even though our actual native population is not having too many births. We're actually pretty stable with the births and the deaths. There are two mathematical models of how populations actually grow. The first one is exponential growth. This is the type of growth you see under unlimited resources, so under ideal conditions. So when you have unlimited food, unlimited water, unlimited space, you're going to see your population grow exponentially. So exponential growth occurs when the population is reproducing at a constant rate. So it is staying constant, it keeps on increasing, and it's never going to stop. So exponential growth is a population just gets larger and larger and larger and larger, and it's going to rapidly keep getting larger and larger, and it's never going to slow down. Exponential growth has this characteristic J-curve shape. So you have two graphs here. The left one is looking at population of bacteria. The right one is looking at elephant population. Notice both of them are showing exponential growth, the J shape. However, look at the time difference. In the bacterial population, you're looking at only 6 hours, and went from about 1 to over 200,000 bacteria in just 6 hours. However, for the elephant population, it went from about 1 million elephants all the way up to 20 million elephants. However, that took 750 years to do that. So you can see exponential growth depending on the length of the actual life cycle of the organism. It can take quite a while for you to see that growth. So the question is, can populations really grow exponentially? Can a population really continue to grow forever, increasing until never ending, just all the way up to infinity? So what do you actually think about that? Hopefully you came up with the answer no. So as resources become less and less available, eventually you're going to start running out of enough food for people or for organisms, enough water, enough space, enough shelter. Eventually it's going to start slowing down until it eventually pretty much stops. The result, instead of looking like a J curve, it makes more of an S-shaped curve. So when you start running out of resources, you make an S-shaped curve. This X-shaped curve is known as logistic growth. So exponential growth is the J curve, unlimited food, water, and space. Logistic growth makes an S shape, and this is when you start running out of resources. So this is the type of growth that you'll see in nature, because eventually you're going to reach a certain amount of individuals that you cannot actually support. However, you notice from like 0 to 18 hours, it is showing exponential growth. So almost all the time, eventually you'll see a population switch from growing exponentially to eventually leveling off and showing logistic growth. That actual number, or the about the number that the graph reaches when it's growing logistically, is known as the carrying capacity. So the carrying capacity is literally the amount of individuals that the environment can hold or carry. So it's the amount of the individuals that can actually be supported in that environment. So the carrying capacity is how many individuals can be supported in that environment. So in this case, look at this graph. You see that it's starting to level off at about 6.7. So that would be the carrying capacity of this yeast population. However, carrying capacities can change. On the test, there will be questions which of the following could change the carrying capacity, if at all. If you, let's say there's a natural disaster, or let's say there's a disease and kills off a whole bunch of plants. Well, you just lost food for your population, so the carrying capacity is going to decrease. So the carrying capacity can go or change quite a bit. And also let me make it clear that at the top of the graph, it is not just going to level off perfectly. You cannot shove the baby back where it came from. So usually at the top of the graph where you see that starting to level off, it's going to go waving back and forth, up, down, up, down, up, down. Because every time an individual is going to be born, there's going to be too many and some are going to die and it's going to dip back below. And it's going to keep alternating up and around that carrying capacity. So the carrying capacity is an average number. It is not an exact number. The last thing I want to discuss is what are the actual factors that limit population growth. They're called limiting factors because they cause the population to be limited. So they're decreasing population growth. There are two types. The first one is known as density-dependent limiting factors. So these factors operate when the population is large and very close together, so highly dense. What are the examples of density-dependent factors? You have competition. The more individuals fighting over the limited amount of food, it's going to limit how big your population can get. Predation. More predators, eventually is going to lead to less prey, and it's going to keep alternating back and forth. Parasitism. When you're clumped together, it's easy for parasites to jump between hosts, so they can spread a lot easier than if they're wide apart. And finally, you have disease. Think of the school, you're 1,600 of you shoved in a very small area. Disease just jumps all between you. You get sick, you get a cold, it goes to your friend, it goes to your entire class. So density-dependent limiting factors are the ones that are usually biotic factors. They're usually living, and their effects increase the more dense your population is. So if you're living out in the middle of the prairie in Kansas, it's really hard to get certain diseases because you're so far apart from other humans. And finally, the last type of last type of limiting factors are density-independent limiting factors. So these are the ones that affect the population regardless of population size. It doesn't matter if there's 100 people in the area or 1 billion people, the effect is exactly the same. These are usually abiotic factors, such as weather. If there's a drought, it doesn't matter if there's lots of people or a few people, there's still no water, nothing, it's going to affect the population just the same. Same thing like natural disasters. If there's a tornado, the tornado doesn't turn to find a whole bunch of people standing around. It has its path. If you're standing in front of it, oh well, you got caught up in it. So they're independent of how many people are in front of it. Seasonal cycles, sometimes the weather changes. That's once again independent of the amount of people in the area, amount of organisms, and certain human activities. So once again, density independent limiting factors are abiotic. They're usually non-living, and the most common example of them is some type of weather condition.